Today we're going to do section 8.4, which is on page 271. First, let's look at the book. Let's see, we have, this is the old page, which is, why am I not getting it to come out? No, this way. Okay, that looks a little better. But mostly we just need this part, I guess. That should be good enough. Next, page 272 and 273. Let's see, all right. Like a little closer, like maybe like that. Okay, and then a little bit closer on the top. And closer on the bottom. Good enough. Next, page 274 and 275. We have right. Okay, right. Let's see here. Okay, a bit closer on the top. And closer on the bottom. All right. Lastly, to page 276. And that, and let me see, is this not level? There. Let me see if that's better. It still doesn't seem very level. I guess it's tolerable. And 276. And a little closer on top. And closer on the bottom. Let's see, is it close enough on the bottom? There, that's better. Okay, a bit closer on the top. Okay, that should do it. So let's start on page 271. Now the problem with the L'Hopital's rule is that sometimes the differentiation might be hard to do, or may even make things worse instead of better. And I mean, the L'Hopital's rule just says take derivatives, right? And then there's no guarantee the derivative might be hard, or maybe it got even more complicated. There's just no promise. So then we also come up with other tricks of calculating limits. And specifically, the indeterminate form where we have infinity over infinity. So the first method we want to do is subsection 4.1, which is the method of series. What series is that? It's the Taylor series. So the Taylor series is, let's turn to the next page. Okay, page 272, and look at theorem 5. Now, theorem 5, we have the conditions where f and g is cn plus 1, so it's perfectly differentiable for the most part. And then, but more importantly, the case derivative from 0 to n are all 0. Okay, so it's 0 all the way up. And then but the n plus first derivative is not 0. These are three very specific conditions. Now, if that is the case, then the limit of f over g is the same as the limit of whatever the derivative that wasn't 0. And we can just calculate that. Now, the proof is very short. To prove it, we have to go find the Taylor expansion formula, which is on page 43. So here is the Taylor expansion on page 43. Okay, here. I mean, you can see it's page 43 up there. Why isn't my camera focusing? There. Let me move a little bit. Come on. Okay, here it is. Now, so let's look down here, the Taylor expansion. The theorem 11. Okay, we have then, let's see, the theorem 11, then we have, here's the Taylor expansion, just to refresh our memories. F of x equal to this sum. And remember that in the theorem we're trying to prove fk equal to 0 from 0 to, for n goes, k going from 0 to n. So this is all 0. So the only thing we have left is this thing right here, where we have the f on the inside, and then, and then so the thing we're proving, then this equals, okay, when we plug the Taylor expansion into right here, okay, into this thing, what we get is that then it will be equal to the stuff on the top and stuff on the bottom. And the stuff on the top and bottom works in such a way that we can, what happens is we can then pull this out, okay, out of the by the mean value theorem. So we can pull this thing out for f, and then a similar one that looks just like it for g. So, and then once you divide, then the rest of it cancels out, and we get, as a result, then we get this this equation right here, okay? Because we used MVT to pull just the f part out of the equation. Right over here, let's see. I'm waiting for my camera to focus. There it is. And now this MVT is on page 162, which means which states that you can pull out part of the integrand and leave the rest if it's being multiplied together, as it is in the Taylor series case. So please work through this yourself, okay? And look at page 162, where it allows you to pull out and the part that's inside and cancel out the rest. So with the MVT, then we come up with this equation, and then and bearing in mind that the denominator is not 0, because if the denominator is 0, then we got a problem. It's not 0 because of we said so right here, okay? And being that it's continuous, and as long as it's close enough, it is not 0, because it's not 0 at A, it's not 0 in some small neighborhood. So therefore we got, so at that point, then we can just let x approach A, and we are good to go, because big X and big Y are in between values. Okay, so that is how Theorem 5 is proved. Now the next thing is, we should comment that if G is equal to, G at A is equal to 0, okay, and then, but the next derivative is not 0, but, and then we have a situation where we might have a situation of dividing by 0, which goes to infinity, which means that we don't even have to consider it much, okay? It just goes to infinity. So please think about that and go over all this yourself very carefully to see if the whole thing makes sense. And let's move on to the next sentence. Then the next sentence is, let's see. So next, there's a comment that says, when the Taylor expansion of given functions are known, then we can calculate limits in the form 0 over 0, and without any differentiation. Okay, the reason is because the differentiation was already done during the Taylor expansion. That's why. So let's, for an example, let's look at example A. Now, example A, we calculate this limit, but we're not going to do it the old way. Okay, we're going to do it by doing the Taylor expansion. Now, the Taylor expansion, if you are to look it up, of this function is equal to that thing. Okay, and all we're going to do is just take this, divide it by that, and the rest don't matter. We only care about the first term, and so that matches. So this divided by x cubed is equal to minus 1/6, okay? And that is the answer. So that is how, so Taylor expansion, if and when it applies, it works out very, very nicely. So basically what we're going to do is replacing f and g by the first non-vanishing terms of their Taylor developments. Now that will become more, you get used to doing that after a while. Okay, so we'll do a bunch of these problems in the homework so that you get used to it. When you do this kind of problem, you just look up Taylor expansion online. And that in the book, what did the book want us to do? The book wants us to look it up in some table, okay? Now we are, how many, 80 years later, our table is called Google. Okay, so you just look it up on Google, you type in whatever you need the Taylor expansion of, and Google will spit it right out at you, and as I will show you later. And then the problem comes out pretty nicely. So next, let's look at example B. Well, please do example A, of course. Now, next, let's look at example B, which please also do this yourself. It's a matter of cranking out the Taylor expansion. Where is it? Okay, so example B, as to do what the book says, okay, let x equal to 1 over y, and then we crank it in and equals to that, and so on. And so then after some algebra and the Taylor expansion, okay, look up the Taylor expansion, then we come up with the answer equals to 1/2. Or we can even expand it in a somewhat different way, and that come out with the same answer, of course. So either method is fine. So that is example B. Next, let's look at example C. Where is it? And oh, one thing I should mention, let's look at the following page, page 233, is when we do Taylor expansion, we need to pay attention that the series is actually converging where we're going for, okay? That part is important. And then, sometimes the series is not converging, and then if you plug it in, you're going to come out with a weird answer. For example, if you were to calculate this thing right here, sine x over x, that's a familiar calculation, but the question is, but if you were to plug in the Taylor expansion for sine of x, which is right here, okay, is just put the minus x on the other side, and if you do that and divide by x and do the Taylor expansion, you might come up with a weird answer. Let me see. What does it equal to? Oh, you might not. Does that still work? Let me think. No, it doesn't work. What happens is you're going to end up with a fallacy. I forgot what I was saying. As this is not going to 0. See, for a while there, I thought we were going to 0. No, we're going to infinity, which means this is going to go to 0. But if you were to use the Taylor expansion, not caring that about the radius of convergence, then you're going to have this. It will end up being 1. Okay, and so please look at that and see where the problem is. And why that method doesn't work. The thing is, if x is approaching, while the sine does, this expansion works for all real numbers, right? But it doesn't work for infinity, okay? It only works for any finite number. So that's why if you approach infinity, that's just not going to happen, okay? It only can approach into any finite number, however large it might be. So please think about that, okay, why that has a fallacy in there. And then we'll move, let's now move on to example 3. Example 3, we have this particular thing. Okay, let me see here. So for example 3, we're calculating the limit. Not much going on, actually. Example 3, we just look at it. We just plug in the Taylor expansion, and everything works out very nicely. Okay? And we only care about the first term, really. The rest of the Taylor expansion don't matter to us. So the first term, once we cancel stuff out, then we get that exact answer. And I will also show you the Taylor expansion. Oh, I forgot to show you the expansion for example B, which is, okay, here's example B. And then, so that's the Taylor expansion for what we did in there. And the way I find it, I just type it into the Google, okay? Square root of x, expand the Taylor expansion for square root of x plus 1, and then it showed me all that stuff, which I copy and pasted here to show you. And next, example C, same thing. We have cosecant and sine cube. We don't really care. Okay, let's just type in the expansion, and we only care about the very first term that matters to us. So after doing some algebra, then so that's how example C works out. The next, let's look at example D. So by now you're probably thinking, oh, we just have to type in the Taylor expansion and get the answer from Google. This is a easy section. Not really. So far, it's taken me twice as long to get through this section compared to the others. So even with a faster way of getting Taylor expansion, this is not a fast section. Anyway, let's look at example D, where we are supposed to show if the function f of x, which is e to the power minus 1 over x squared, is continuous at 0. Well, in fact, it's differentiable at 0 if we define it as 0 to be 0. Okay, now that is, we have, did I plot this thing? Let me check. Well, I didn't plot it in here, but I plotted this graph several times in the past. It's that graph, my favorite graph, where you go along at 0 and then suddenly it goes up and then goes down and then it becomes 0 again. And the function is infinitely differentiable. So, especially at 0. So it is my favorite graph, but to prove that it is at the top it goes to 1, but to prove it is not that simple because x being in the denominator and all. So we're going to come up with a trick to do it. The trick then is, let's look at this, okay? We'll calculate f prime, of course, is a continuous, except at 0. And then at f prime 0, we'll go back to the definition to calculate it, which equals to something. And then as the limit of the value goes to, h goes to infinity, this goes to 0. But how do we prove that? It's not obvious. Now, to prove it, we have to use a trick right here. See, we have to let t equal to h to the power of negative 2. That's replace most of that stuff up there. That is, let's see, t equals to, now give me a second here. Something is looking odd. Never mind. I was just thinking about the wrong thing. Anyway, so once we let t equal to h to the power negative 2, which means h is equal to some square root of t, 1 over square root of t of something. And this thing cleans up to become this. And this is easy to do with the L'Hopital's rule. Okay, we can quickly prove that this goes to 0. And making this substitution, you might think, why don't we just apply L'Hopital's rule right here? Well, if you do, it would have been useless. So, so I didn't trust the book. Okay, so I did that. I did exactly that without it. And so please do this yourself. Okay, and you notice that when I tried to apply the L'Hopital's rule, I think right here. And I applied the L'Hopital's rule, and I got nowhere fast. My result is exactly the same as what I started with, or something like that. Anyway, I got nowhere. So then I had to agree that the book is right. Okay. Whereas the direct application of the rule would have been useless. All right. So we applied this rule, and everything worked out. So then f prime of 0 is also 0, which and then the limit of f prime of x, which is this thing, as it approaches 0, is also 0. So then that will prove that f prime is continuous. Okay, and so calculated the limit, and that equals to, and that does equal to 0. So we prove that f prime is indeed continuous. And with the same method, we can prove that f is any kind of derivative is going to be continuous at 0. Which but we're going to skip that because that just sounds like a lot of repetitive work. And so here's some of the stuff I wrote down for f prime to show f prime is continuous. Then we use this trick again where t is equal to 1 over x squared or something, so that the limit goes a lot better. And even then, we have to differentiate 2 times to wear the t down. Okay, so the t's power get worn down each time until the t has to end up being on the bottom, and then everything works out. So the more derivative you have, then the more times you have to differentiate until you finally get to the end. But it works the same way as the second derivative, no matter how high a derivative you have. So we will just go with that, okay, and not think too hard about it past that point. So let's look at the next page. Now we're on page 274. Now let's consider subsection 4.3, orders of infinity. The now we consider f and g are two functions. Okay, they both become infinite positive. We'll think about positive for now. As the variable x approaches something, whether it's a finite number or infinity, doesn't matter. It approaches something, but what matters is f and g are both going to infinity, which means we're considering an infinity over infinity situation. Now we're going to introduce a new symbol. Okay, that symbol in the book that looks a bit like less than, but it's bent. It's a bent less than symbol. So then we'll call this. This symbol means if f of x is bent like less than g of x, this symbol is pronounced weaker. Okay, so if f of x is weaker than g of x, that means the limit of f of x over g of x is equal to 0 as x go to wherever we're talking about, be it a certain point or infinity. So then the relationship, so it's pronounced as f of x is weaker than g of x. Now if x goes, for example, as x approach infinity, then the log x to the power 10 is going to be weaker than the 10th root of x. Now that should be readily confirmed. Please do that yourself, as I have done here. If I can find it, let me find it. Yeah, right here. See, I have a log base of 10, and then to divide this, just apply the L'Hopital's rule and some 10 times or something like that until we finally got to the point where there's nothing on top and just 1 on top, and it equals the constant times x to the power 10th. And so please do this yourself. It's just a matter of doing the L'Hopital's rule 10 times. But you don't actually do it 10 times. You just pretend to do it 10 times. Because who wants to do that 10 times anyway? So then there is that proves that the log x raised to the power 10 is weaker than the x in the 10th root. Sorry. Okay. So in general, we have a table here that is fairly obvious, so I'm not going to bother proving it, but that log of x is weaker than log of x, which is weaker than x, which is weaker than x e to the power x, and then e to the power x. Okay, so that is a list of weak stuff. So we can always make things weaker by slapping on another log, and we can always make stuff stronger by putting an e under it. Okay, just push it up, and then so you have a string of e's on top. On the other side, on the weak side, you have a string of log, and you keep saying that, and then so the thing got weaker and weaker. Okay, and there's another point where I wrote. So this is an important point, and that will be needed in the homework. But the next sentence afterwards is also will be needed sometimes at the homework. So I wrote down the circle 1 here to refer to it, because the book didn't give it a specific, I don't know, title or something. So we'll call it 1. The order of any infinity is increased by raising it to a power p bigger than 1, and is decreased by reducing it to a power less than 1, but bigger than 0, of course. So this, with this, then we can put stuff that's in between that list, okay? Which the book calls it a table. That's well, I like to call it a list. That doesn't look like much of a table. It's just a one line. Anyway, so let's look at example E, okay, to see what we're gonna put in here. First, example E, we need to prove that thing. That is, I think that is a fairly straightforward thing there. Yeah. So please do example E yourself, as I have done here, by just using L'Hopital's rule, really, and everything will come out. What is that? Well, anyway, just use L'Hopital's rule, and you should be doing okay. Next, let's look at example F, where we are to find an infinity stronger than all functions x to the power p, where p is up to 1/2, but less than 1/2. So this function has to be stronger than x to the power p, but it has to be weaker than x to the power 1/2. It's stronger than anything less than 1/2, but weaker than 1/2. I mean, how's that well, how are you supposed to come up with that? And I tried to come up with it. I couldn't think of anything. So the book says, well, such a function is square root of x over log of x. Okay, and then we proceeded to prove that that is true. Now, if you look at this, yeah, there's the proving it is very, very simple, I think. Well, okay, maybe not simple, but doable. So at this point in our lives, if something is doable, it's simple. Okay, and so then f of x, then we work out the algebra and check it with L'Hopital's rule or whatever, and we're able to prove that it indeed is f of x is indeed stronger than x to the power p, but weaker than square root of x. And my question, however, is how did they come up with this? And the book doesn't say, so my suspicion is probably these are people who don't have a date on Friday night, so they just mess with all kinds of functions until something actually works out. Something like that. And yeah, anyway, so that's problem 5. And I think that's quite interesting that you can squeeze a function right in between those two things, which doesn't seem to have any space, because p can go all the way up to 1/2, but isn't 1/2, right? And whereas square root of x is 1/2. So you shouldn't, how would you be able to squeeze something in between? And yet they did. This function actually works. I mean, it's quite neat. Okay, so that's example F. Now next, let's consider example G. Now example G is going to show you a trick, which is we consider e to the power square root of log of x, or x, which one has the higher order, that is, which is stronger and which is weaker. Well, to do that, what we have to do is remember that if f is weaker than g, then e to the f is weaker than e to the g. And that can be proved. I will show you in a moment how to prove it, but please prove it yourself, because as the book says, it can easily be shown. Okay, so try to do that yourself first. Now, with that fact, then we just have to prove that square root of log of x is weaker than log of x, like this. All right, so I'll just show this to you. This is example G. All right. Yeah, I think so. And I don't have example G here on the next page, right here. Okay, so example G, first we proved that f weaker than g is e to the f is weaker than g of e of g by this simple trick here. Well, I don't know how simple it is, but by this trick. And so once you prove that, then the next thing we can prove is that e to the log x is over here. X is just e to the log of x. Okay, this is e to the square root of log of x. So this is weaker than that because now we compare the exponents. Because we just proved that the exponents one is weaker, then the slap the e under it is also weaker. And this is weaker. How to know? We know this is weaker by number 1 on page, statement 1 on page 274, which is what we just did. Let's see, where did it go? Right here. And yeah, where we did right here. See, log of x is weaker than x. Is that what I was talking about? I forgot. And let's see, what are we talking about? We're supposed to prove square root of log of x is weaker than x. Never mind. So we need to prove that square root of log of x is weaker than x. Square root of, okay, we have log of x is weaker than x. Let's see, what am I talking about? Square root. You see, all these square roots are confusing me. I need to keep my mind straight. Oh yeah, the statement isn't that. Well, the statement is this sentence right here, which I want you to bear in mind, is that the order of any, what does that say? Wait for my book to focus. Come on. The square root of any infinity is increased by raising it to a power bigger than 1, and is decreased by raising a power less than 1. Therefore, That's what I was wanted to say. Therefore, the square root of x being raised less than 1 is weaker than the function log of x itself, okay? Because it says so. If we raise it to any power that's less than 1, it will become weaker. So this is weaker than that, which means this function is weaker than that, and that is what we got our proof going. So that is example G. Please do that yourself. And then, next, let's, where am I? Example G. Okay, example G. So bear in mind, this sentence in example G, this fact, okay, that f is weaker than g implies e to the f is weaker than e to the g. Please make a note of this. This is going to be useful in some of the homework problems. So next, we'll look at example H. We have a bunch of stuff here, and we need to order in a bunch of increasing strength. Okay, so then we just, in this case, we can just use example G. That is, we'll slap the e under, we'll just look at their exponents, okay? Turn everything into exponent form, and then compare the exponents. If the exponents are weaker, then the original form is also weaker. So that is what I did here. So please do that yourself, okay? And we'll go to the next part. Example I. Now let me look at this. So example I is another calculation, just like we have done so far. And so here's what I did by using some of the stuff that we did before. And then I also did some of the L'Hopital's rule. But anyway, it all worked out. And then the book did it slightly differently, which nothing wrong with that. So please pick either one method is good enough, okay? And it's not necessary to do both, but if you have time, doing both is even better. So anyway, that is that. Now, of course, when we are evaluating limits, sometimes we come up with something that doesn't even go to 0. It just goes to a fixed number. Then, of course, we can just ignore those because they don't affect anything at all. And then the next thing is, the next part is talking about prime numbers. Now this part is a bit of a, let's just say, mathematical gossip, okay? The author is telling you some facts about the prime number that Euler did. Euler is the greatest mathematician of all time. So Euler figured out some facts that is somewhat interesting, like all gossip. But we're not going to prove, the book is not going to prove any of this, so I'm not going to describe it in great detail. You can just read it yourself, being that there's no proof, so it's just a bunch of facts to read. And but we're not going to need it in the homework either. It's just an interesting tidbit. And the last thing we should mention is that the reciprocal of an infinity, I'm reading at the last paragraph right here, okay? The reciprocal of an infinity is called an infinitesimal, and that we can even classify infinitesimals according to their strengths. And that is, infinitesimals is just 1 over infinity. And therefore, the stronger the infinity, then the, well, I don't know if you want to call it stronger, that is closer to going to 0 faster, the infinitesimal. But let's not bother with that, because we'll just transform all infinitesimals into infinities, okay, like the book says. So, and not worry about infinitesimals, because that's just another way of saying the same thing. So having said that, let's look at the last example, example J. We have a bunch of stuff here, so let me see. Example J, we have, I don't think there's any particular tricks here. So here's what I did, and so please do that yourself as well. I guess specifically, you can refer to example B on page 268, and we are on page 271. So that's a few pages ago, where we already calculated x cotangent x. So you can save yourself a couple of steps. But anyway, this should work out nicely. So that means we have come to the end of this section. For homework, please do problems 1 to 15, and then also problem 19 and 20. Specifically for problem 19, please plot the graph of the function. Okay, I don't normally care if you want to plot the graph. You can plot it if you feel like it. And when I say plot it, I mean use the Desmos calculator. But problem 19 is I think it's worth plotting. So I ask you to plot the graph for specifically for problem 19. And then I think problem 11, I will post a hint for problem 11 and problem 14, and then you can look at the hint later. Okay, after I will post it below the video description. I mean in the video description below the video. So that is so please go do your homework, and then I want to talk about them. So first, let's look at problems 1, 2, 3, and 4. Okay, I don't think I had any trouble doing that. It's just a matter of plugging in the Taylor expansion, and things worked out very nicely. This is problem 1 and 2. Okay, and yeah, I think well, anyway, that's problem 1 and 2 for your reference. And then here's more of problem 2, and then problem 3, which is the Taylor expansion, and then problem 4, which has this thing right here. That's the hyperbolic function. You don't have to know what it is. Just find out Google what the Taylor expansion is and plug it in. Okay, then you'll be good to go. And that's so that is all the answer. Now I also here are the Taylor expansions that I Googled, and I typed it out right here for problems 1 and 3. All right, and then for problems 2 and 4. So here's for problems 2 and 4. Here's problem 4. I think problem 2 doesn't have a Taylor expansion. Here's the Taylor expansion for problem 4. Again, I just Googled it and copy and pasted what this stuff does. Basically, that's all you need to do. It doesn't even matter what these things, what arctan or this is the cotangent h, the hyperbolic function. Doesn't matter what it is. Okay, we'll just plug it in. And then problem 2, being that we don't have an answer at the back of the book, I plotted the problem in the Desmos calculator to prove that this does go to infinity as x goes to 0. Okay, and maybe not prove but confirm. And then problem 4, I confirm this confirms that as x goes to infinity, then this thing goes to 1 as I calculated. This is just being that we don't have the answer at the back of the book, so this helps confirming that our answer is correct. So that's that. So next, let's look at problem 5. Problem 5 has a slight trick to it. What you do is you use both. That is, you use L'Hopital's rule, then you use Taylor expansion, then everything comes out nicely. Okay? At first I was having trouble, and then I realized I just have to use both methods. So first, using L'Hopital's rule gets us here, and then with this, then we're able to expand it by Taylor's expansion. And with that, and then the answer comes out very nicely. And we have, I also have the Taylor expansion plotted right here. Now let's see, yeah, right here. There's the Taylor expansion. Okay, and once I was done, I plotted the original function into the Desmos to make sure that it does go to where it's supposed to go, which is positive 5, I guess. And the Desmos confirmed that I was on the right track. Now notice Desmos also draw a blue line right on the y-axis as part of the function. That's just because of a calculator precision error. That is, calculators, they are not able to do certain things. So then they might end up have an extra blue line there, but it doesn't belong there. Okay, the function does go to 5 as it approaches, as you can see. In fact, it can be defined as continuous at x equal to 0 if we define the value to be 5. So next, let's look at problem 6. I think it's a similar deal. The problem 6. Let's see. Where's problem 5? Okay, Problem 6, yeah, that we just figure out what the Taylor expansion is, and the answer comes out in one line. As to find the Taylor expansion, we just type that thing into Google. Okay, so the Taylor expansion of that whole thing, okay, 2 over x, etc. Type the whole thing in, and Google will tell you what the Taylor expansion is. And then I came up with the answer 1/6, and then I confirmed that when we type the original function in, see, it does go to 1/6 at 0. See, they intersect very, they are tangent to each other very nicely. So that is, which confirms that my answer is correct, even though this problem doesn't have an answer at the back of the book. We can, most of the time we can plot the graph. If we don't have the answer, we can just plot the graph and see where it goes. Okay, it gives us a good idea of what to look for if we're having trouble finding the answer. That is, problem 8, what was I talking about? 7. Okay, problem 8, it also is a direct application of Taylor expansion. In fact, problem 8 has an integral in there, but that changes nothing, okay? Because we can actually calculate Google can actually do the Taylor expansion of some integral too. That's how smart it is. Right. See, I have it right here. We have the Taylor expand problem 7. I guess I didn't show you this. But anyway, the Taylor expansion of that integral. Give me a second here. Right, I forgot to show you the Taylor expansion of the integral. To get it, you just type it in, okay, in Google like anything else. See, I have a screenshot of what I typed into Google. I typed in Taylor expansion of integral from 0 to x of e, etc., etc., and Google popped this right out for me. How nice, okay? Then you plug it in and the answer pops out right away. And so next, problem 8, a similar story. We have the integral of we need the Taylor expansion of the integral of cosine squared, which I got right there, okay? And then the arc sine, which is given right here. Now remember, the integral of cosine squared at 0, cosine 0 is 1, so the function is continuous there. So nothing weird is going to happen, okay? If we do the Taylor expansion, everything is perfectly okay at 0. So that here's the Taylor expansion at or near 0. And then, as you remember, we have to be careful that our Taylor expansion actually converges. Otherwise, we're just babbling nonsense. Now, problem 8, once we do all this, the answer is that it goes to infinity. As I also plotted the graph into decimals and to show that it really does go to infinity. But the book gives a different answer. I believe the book is wrong because I got this from expanding the Taylor series, which do converge, and then yeah. So I believe the book answer is wrong. That it should go to infinity instead of the 2 over 9 or something like that. The book says, because that doesn't really make sense. Because this is just a short little Taylor expansion problem, and I don't think there's any trick in here, in the sense that these things, both the numerator and denominator converges properly at 0. So there's, I don't think there's anything unusual happening that should make anything bad. Okay, this is just arc tangent. Yeah, so I'm pretty confident that that I'm right in saying that this series goes to infinity, and the book answer is wrong. Which is unfortunate because, well, I think that what happened is, well, it doesn't matter what happens, okay? That's all I have to say about that. So next, let's look at problem 9. Problem 9 is, problem 9 is some fairly short calculation, although I did try some things that didn't work, but eventually I realized that is, this is equal to, well, we consider this fact, okay? Since this is equal to 0, then everything does work out nicely. So that is, yeah, that's that. And the limit does go to 0. And then, and I also confirmed that by plotting the graph into the calculator because this may not have an answer. I don't remember. Doesn't matter. I always plot it in if the problem is a bit hard to tell. So because Desmos then confirm my suspicions that this is indeed going to 0 as x, in this case, x is going to infinity. So that's that. Right. What happened is for this kind of problem, we slap a e under x, okay? And then turn it into this. So the denominator now is written as this, with the e to the power, and then there's a log of x, and so such that this is the same as that. But now we have a e in both positions. Then we can use the example G, where it mentions that if the functions are weaker, then the version of putting e under them are also weaker. So using that principle, then I just prove that the functions are weaker, which is so therefore the exponents are weaker, and therefore the function is weaker as well. And that is problem 9. Okay. So next, let's consider problem 10. Now, something interesting happened in here, okay? And I want to show you in a moment. Now, problem 10, we have this function, so I did it the same way we always do, and except with a slight trick. There is sign of y in there. Well, sign of y is less than y when stuff is well, that's because it's 1 over x. So 1 over x will change 1 over x into y. And then so then x goes infinity, y is going to 0. And at that point, sine of y is less than y. Okay, that's the graph of sine of y versus y. So then we can just substitute this in and not have to worry about the sine of y. It makes it much simpler. So doing L'Hopital's rule or something, we can quickly calculate. Then we slap on L'Hopital's rule many times, 10 times I think it is, and wear it out until it finally got down to this, which does go to 0, and that the answer is going to 0. Okay, and that should be right. And then let me see, does this, yeah. And then the answer at the back of the book also says 0. But however, then I went to plot it in the calculator, and the calculator says it goes to infinity. Okay, I mean, here's my plot for problem 10. Okay, when I plotted it in, it goes like this. It didn't go straight up. I squeezed this graph together a little bit, but it definitely goes up. So I zoomed out, and then it was still going up. So I continued to zoom out until I got to the 400 million range. Okay, when it is 4 times 10 to the power 8, that's like 400 million, right? And finally, it started turning around. Okay, at 400, it went up, continued to go up, and at 400 million, it decided to turn around and finally started going down very slowly because I squeezed the graph together. This is in the unit of 10 to the 11. That's only 10 to the 8. So that is like 1,000 times more packed. Okay, so that looks more like going down because of it. If it wasn't for that, if you were to even, if the graph is zooming square, then this would just look like it's going level. It doesn't look like it's going down at all. And even then, as you notice, the farther it goes, the less it goes down. Okay, so it's gonna take forever to get to the 0, but it will get to 0. Now, isn't that cool? That something will go up, and for like 400 million before it actually decide to turn around and go down, and it will go down all the way to 0, but very, very slowly. But it will head for 0. I don't think it will ever get there, but it will actually head down. So, that is such an interesting function as a result. Okay, but that is problem 10. So problem 11. Next, let's look at problem 11. Which I was not able to do problem 11 after numerous tries. So finally, I was tired of it. Plus, I was tired. I couldn't even think. This problem was totally wearing me out. So I Googled it, and Google knows exactly how to do this problem. Turns out we need 2 tricks. Now here is how I typed it into Google, my exact wording, okay, in case you want to try typing this. So I described this problem like this to the Google, and it was able to understand me. Look how smart this thing is. It knew that I was meaning this, okay, as x goes to infinity. So Google taught me, well, here's the trick. The first trick is we're going to, instead of calculating the limit, we're going to slap natural log on top of it, so that the whole thing, and so we turn in the multiplication division into addition and subtraction. Can you believe that? Okay, so fine, we'll do that. That's the first trick. The second trick is that we're going to factor out one of these things, and then divide it with all the others. The biggest item out of those four things that we're adding or subtracting. So once we factor that out, we got these things, and then we can prove that each one of these, besides this one, okay, each one of these terms are going to 0 as x goes to infinity. So then the limit, we only have to calculate this one, and this one can be calculated by L'Hopital's rule, which quickly we notice that will go to, that end up going to 0. And so each one of these things will go to 0 with the same L'Hopital's rule. So that then the original limit then is going to be equal to this function, which will go to infinity, okay, as x goes to infinity. And if the natural log of something goes to infinity, then that thing itself for sure goes to infinity. That is, and that's that. So that is how to do problem 11. Boy, was I tired when I was towards the end there, trying to get this thing to work. Yeah, well, just a matter of a matter of the trick, okay. Once, of course, once you realize that you need to slap on the natural log, then everything comes out looking much nicer. So that's problem 11. And next, let's consider problem 12. Problem 12 is right here. Okay, problem 12 right here is let's see here. Problem 12. Well, okay, let me find it first. Now, problem 12 looks quite hard, doesn't it? You got a ton of functions all being multiplied together, but in reality, it's kind of like the author just throw a bunch of junk at us. Okay, it's like go buying stuff on sale. There's a pile of stuff, and at the discount store, and you look at each one, and then come to find out the sine of x over sinh x, it goes to 1. And sine x over that goes to 1/2 if you just apply L'Hopital's rule, and the others are similar. Okay, you don't have we don't even need anything we learned here. We just use the previous knowledge from a previous section, and everything comes out very nicely. And anyway, so the total answer is negative e over 2. The book answer at the back is missing the negative sign. Okay, and I'm sure e equals minus e over 2. Partly because that's how I got it, and partly because I also graphed this into the calculator, and I mean the Desmos, and Desmos says the same thing I said. See, here is problem 12. As you can see, I graphed it in there, the green line, as x approach 0, y approach e to the power minus 2. That's the purple line. See? So Desmos confirms that this should be negative, because it's e. That's what Desmos says, so I'm confident that I have it right. So that is problem 12. Well, I'm running out of time here and getting very tired, and plus I'm hungry. So I will finish this section in the next video.
Oh.